look at what are the possibilities. Number one concept in probability is what I'm showing you right now. It's called the multiplication principle. If you have choices and they're independent of each other, all you do is you multiply the choices. For example, let's say you have 3 physics books, you have 4 math books, and 2 English books. Okay? And you're labeling these each different. They're a different kind of book. They're not identical. Okay? How many different combinations are there? Or I shouldn't say combinations. How many different arrangements are there or possible outcomes are there for these books? So let's say I take this first physics book. I can connect it with this book and this book. So there's one. I could do the same one, and then I can take this English book. Is the purple different than the green? Yep. And so, you know, there's 2. But now if I go for the next one, Math Book 2, there's a situation, and there's a second one. So now we have 2. Oh, excuse me. I didn't do that quite right. Almost. Not quite. Not quite. I'm still on M1 here. So I'm going to use the blue. Okay. And then I'm going to use the yellow. Okay. So there's another 2. So with this first physics book, how many total ways can we connect to the other books? 2, 4, 6, 8. Do you agree with that? Okay. So there's 8 ways that a physics book could connect with those. How many ways can this one connect? 8. This one? 8. And this one, there was 3. Okay. So we have 8, 8, and 8, which is going to be a total of what? 24 outcomes. Ways that you can connect those 9 books if you're going to combine one with each. Well, an easier way to get 24 is to say there's 3 physics books, there's 4 math books, and there's 2 English books. And what do you do with 3, 4, and 2? Yeah, here's your 8, 4 times 2. Here's your 24, 3 times 4 times 2. And I will bring this back a lot of times. It's choice times choice times choice. If you say the word then, or oftentimes and, these words mean multiply. What about or? We'll come back to that one. But for trials with N1 events, N2 events, and N3 events, the outcomes are N1, N2, N3. What do you do with those? The outcomes will be multiplying. And that would continue to those outcomes. Here's a little separate example here. How many ways can we get from A to D? How many different total paths can we take? Well, here's one. What's another one? Well, I can do the same skip here, but then I can go there. I can take the same skip here, and I could go here. So there's 3. And then if I go right across here, there'll be another 3, right? So across the top, how many ways can you go from A to D? There's 2 here, there's 3 here, there's a total of 6. How about across the bottom? We'll go from A to C, it's how many? 4, and then from C to D, it's 3. So this is going to be 4 times 3, which is going to give me 12. Now here's where the or comes in. I can either go across the top or I can go across the bottom. Do you think I multiply these? No, this is going to be where we add. This is where you get a total of 18. But it's still a lot of this multiplying. 4 times 3, 2 times 3. All right, so with permutations, we're looking at order matters. Would you write that? Order matters. Is this helping a little bit? Starting to sink in or come back? So the number of arrangements of 7 students sitting in 3 available chairs. So you have 7 students. How many students can sit in the first chair? 7. Then, see how this comes to play? Then, how many are left to sit in this chair? 6. Then, how many are left to sit in this chair? 5. So if we want to know how many arrangements of 7 students in 3 chairs, it's going to be 42 times 5, or 420 divided by 2 is 210 arrangements. Okay, so you can probably see a formula taking shape. N factorial is going to be, well, let's do 3 factorial first. 3 factorial is 3, then there's 2 chairs left, then there's 1 chair left. 3 factorial is 6. What do you think is 7 factorial? Well, it would be the first chair. There's 7 chairs. It would be 7. Then there's 6. Then there's 5. All the way to 1. This is a big number, whatever that is. 7 times 6 times 5 times 4, 3 times 2 times 1. We sometimes leave that out. So what's n factorial then? Well, it's n times n minus 1 times what? N minus 2 all the way to 1. Do you go negative? Do you go to 0? Why not? Then it would just be 0. And then it wouldn't make any sense with the negative. So we stop at 1. Stop at 1. All right? Permutations. Now, think of this really interestingly as you have 7 students and 3 chairs. Can you kind of see how a 7 factorial is involved here? But what's chopped off? 4 factorial. So, let's put this in the context of 7 and 3. So I get this is 7 factorial. What's 4? What would that 4, 3, 2, 1 that's chopped off, what would that be in terms of 7 and 3? 7 minus 3. You got it. So R is the number of chairs, and N is the number of students. So the general equation, they call it objects and R chosen. NPR is just going to be N factorial over N minus R factorial. Okay, things going all right? Making sense? Yes?
This is assuming that one student sitting in one chair is different from that same student sitting in another chair versus another chair.
Correct, correct. The order matters. So, yeah, we can have 7 students sitting in this chair, 6 students sitting in this chair, and 5 here, but these 3 could be in 3 different, this person, if it's Briette could be sitting in any one of these and it'd be different. Okay. And that's good segue into this next one, combinations. Now we're looking at order. Doesn't matter. Okay, we're looking at the operative word here, groups. So how many ways could I arrange Kaylee and Emily and Sarah? How many ways could I arrange those 3? 6. Because 3 could sit here, then there'd be 2 here, and then there'd be 1 here. 3 times 2 times 1 is 6. How many groups of these 3 are there? There's only 1 group. Doesn't matter how I place them, they're still going to be the same. Well, how many, if there's only one, how many ways could we arrange these three so they're still the same group? 3 factorial, right? So what essentially you're going to do is if you're looking at number of groups of 7, you do these, by the way, I call this the slash method. Sounds violent, but it's not. I use slashes, and this tells me how many locations there are so I can set up my multiplication deal. If I have 7 students, 3 available chairs, there's 7 that can go here, then there's 6, then there's 5. But with those 3 chairs, how many ways are there that we could arrange them and they're still the same? Like if I had Emily and Kaylee and Sarah, how many ways could I arrange those 3 and still be the same? 3 factorial. So I'm going to divide by the number of chairs factorial. Because they're still the same, right? So that makes sense, because if you had 3 people and 3 chairs, 3 could sit here, 2 could sit here, 1 could sit there, and then we're going to divide by 3 factorial. That'll give me 1. But this one won't be 1. It'll be a little bit different. So now when we look at combinations, notice the same thing we had before. N factorial over n minus r factorial is still happening. 7 factorial, chop off 4, 3, 2, 1. That's what this is. But we're also going to chop off what else? We're going to divide by what? R factorial. So it's kind of nice. Little formula. So now we got a couple other considerations, repetition and circle. First thing with repetition, what if you have 2 that are identical in here? How do you handle that in the probability? Well, how many ways are there to arrange, we'll call this apple 1 and apple 2. How many ways to arrange these 4? How many ways? 4 factorial, 24, right? So let's list them out. This will be fun. O, A1, A2, and B. And then we can have O, A1, B, A2, right? We could have, let's just keep doing this. Let's move the B through here. Or do I want to do it that way? No, let's do it this way. O, A2, A1, B, O, A2, B, A1. And now let's put B next. B, A1, A2. And then we're going to have O, B, A2, A1. Does this look correct? Does this look right? Because notice I have 2 B's here, 2 A's here, 2 A2's here, A1. I have 2, 2, and 2. I have 2, 2, and 2. So it looks great. Now, which of these are, is there one that's the same as this? Yeah, it's the third one is the same. Are there any that are the same as this one? Fourth one. Yep. And then are these last 2 the same? Yep. So what did that do to my total? Reduced it by 2, didn't it? Reduced it by 2. And what if I had, you know, A1 first, A2 first, B2? It still would be half, right? So do I need to do the other 3 sets? No. So essentially what happened here is we took this total n factorial and we divided by the repeaters. And in this case, it was 4 factorial over 2, which is just going to be 12. It's going to be a total of 12 different ways to organize those. And this is just n factorial over n 1 factorial is what this would be. The number of repeating these. By the way, is that the same as dividing by 1 orange factorial? and 1 banana factorial. Is that the same? It is. 24 divided by 2, it's still 12. So all you're doing with identical things is you're doing the n factorial and you're dividing by the repeaters. Or non-repeaters, but I wouldn't bother with the non-repeaters. They're just 1. So just the repeaters here. And this is actually kind of helpful. Did I have an example here? Let me give you an example. Mississippi. How many ways to arrange these letters? Okay, so arrange these letters. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 factorial. Are there any repeating M's? No. I's? 4 factorial. Repeating S's? 4 factorial. Repeating P's? 2 factorial. So you probably want to know how to do that in your calculus. When you go to math, you go to probability. If you see a problem, okay, let's see here, get out of here. So I'm going to go over to probability. Each column, probability has all of these. And so let's say you want to do 11 factorial. So you start with, I forgot to do this, put in 11 first. Then go math, arrow to probability 4. Now it's 11 factorial. Then divide by 4 factorial. Can I just put 24? Is that okay? Then I'm going to divide by another 4 factorial. And then I'm going to divide by 2. And that should give me 34,650 ways to rearrange the letters in Mississippi, excluding those when the I's are in the same places. That took care of all of those. Compare that to 11 factorial. Math, prob, 4. 11 factorial is quite a bit larger. Okay. Real quick, let's do the 7 choose. It was 7 with 3. So we're going to do 7 and then go math, probability. We're going to look at the arrangements, which was 2. And we had 3 chairs, remember? So we said that was 210, didn't we? Yeah.
For the first one, why did you divide by 24 and divide by 24?
Oh, this is the Mississippi one where we were having repeating S's, P's, and I's.
In the equation, it looks like you're multiplying them.
Oh, thank you. In your calculator will either allow you to put these in parentheses and divide it into 111 or 11 factorial, or I would just take 11 factorial, divide by 24, and then if I multiply by 24, that would cancel out, wouldn't it? So you just do, because it's in the denominator, you divide, you divide, you divide. Good question. So this one was 210. Now let's do 7. How many groups? Will there be more or fewer groups? I think it'll be fewer. So let's see. I'm going to go to NCR this time. This is the number of groups. And when I put in a 3, it should be 35. It is Pascal's triangle. Pascal's triangle can all be written as combinations, every single coefficient. All right, quick little, this is the assignment. We're going to do a couple of these together. There are 4 letters to be placed in 4 letter boxes. How many ways can the letters be mailed? If only 1 letter per box is allowed. Okay, 1 letter per box. So how many can I put in the first box? 4. How many are left to put in the next one? 3. How many are left to put in the next one? 2 and then 1, right? So this is going to be 4 factorial or 24. We like that. There are no restrictions on the number of letters in the box. Yes, that's right. Good, Ann. So you could put 4 in the first one. What could you put in the second one? 0 through 4, yep. And so we put 4. We could put 4. We could put 4. So this is just going to be 4 to the 4th, which whatever 6, is that 256?
You could do 0 as well.
Great question.
It doesn't technically say you need to do all of that. I mean,
Right.
unfortunately, right.
Wow. Okay. Consider the cubic polynomial ax cubed plus bx squared plus 5x plus c. If the coefficients a, b, and c come from the set -3, -1, 1, 3, find the number of possible cubic repetitions or cubics if no repetitions are allowed. So for this first one, how many could you put in the first position? Yeah, there's 4. And then the second position. 3, and then 2, and then 1. Yep. So there's your 4 factorial again. Interesting. Then it says find the number of cubics if the coefficients now come from -3, -1, 0, 1, and 3. Because we could have that. Oh, did I do that wrong? Because there's only 3 there. That's okay. I didn't change anything. But there's only 3. So how many possible values could go in the first one? You'd think so. It's not a qubit. So it's a little trick question. That's what makes probability hard, is that situations require different thinking. You can't have a 0 here because then it wouldn't be a cubic. So how many are left if we don't have the 0? 4. Now, how many are left to go in here? Careful. 4, because we took 1 out that's not a 0. Including the 0, there's 4 left. So this won't be 4, choose 3. This is going to be 4 times 4, and then this next one will be what? 3. Yeah. So a little different, but I like it. Makes you think a little bit. Puzzle Friday every moment in this stuff, you bet. How many different ways can Susan get dressed if she has 3 skirts, 5 blouses, 6 pairs of socks, and 3 pairs of shoes to choose from? You have slots: skirts, blouse, pairs of socks, and pairs of shoes. How many blouses? And then she wears blouse, socks, shoes, all that. Yeah, so you just take 3 times 5 times 6 times 3. Did I miss something? 3, 5, 6, 3. All right.